I think you know the polarity, right? Just I want to cover this also simple. I'm having two phases like this. If I'm having a polarity of these windings, it seems that the current is flowing into that, I mean, right? So both are in same direction. So it skews the additive polarity, like the polarity. If I am seeing the same connection where the two windings having the polarity, one polarity is this, one polarity is this, then this is the input coming, the flow of the current. Flow of the current is this. So it seems that is a subtractive polarity. I mean that winding or how they are connected. So you know this how these are connected. The coil is connected in this way. For the both, the coils are connected in this way. The current is flowing this. And if you see this, the current here, the coils are connected in this way, but here the coils are connected in this way. The flow of current is opposed, subtractive polarity. Just for example, for just basic understanding of the polarity. So fine, keep all these apart. Let's focus on the vector group. So the vector group of the transformer, as I said, we are having different types of vector groups. In that, mainly if I am considering the phase displacement between the high voltage and low voltage winding. So generally, the vector for the high voltage winding we will take as a reference vector. Displacement of the vectors of other windings from this reference vector within the anti-clockwise rotation is represented, generally will represented by the use of some clock figure. I will show you the different types of things before. Let's then just to focus on what are the different types of we can see. I mean that suppose let's say 0, 1, 11, 5, 6. Suppose these are the, you can see in the clock 0, 1, 11, 5, 6. It seems that 0 degrees, that LV phasor, low voltage phasor, is in phase with the HV phasor. If it is a clock is 1, it seems that 30 degrees lag, I mean, the LV lags the HV with 30 degrees. Rotation is anti-clockwise because I am considering the reference is the high voltage vector. As I said, the reference one is the high voltage vector. So when you're seeing this is the lagging, so LV is lagging the HV by 30 degrees. And if it is a 11 o'clock, suppose it's 11 o'clock, then this phasor is leading the LV leading the HV with 30 degrees. I mean, 330 degrees lagging represents that 30 degrees leading in a simple way. If it is in this way, right? 11 o'clock, the upper one, and this is the one you can see always in this. This is the phase reference. Similarly, for all the clocks, you can see this digit refers the angle which is lagging or leading from the reference vector. Generally, the reference vector we will consider as a high voltage vector as a reference vector in the vector drawings. By this, you can see, suppose I want a 0 degrees phase shift. Why I require 0 degrees? Why I require 30 degrees? I will talk in a while. Just I'm explaining you now how the vectors are connected. If I want a 0 degrees phase shift between the two windings, then I can go with a star 0 or delta 0. And zigzag is also there, but we are not talking about that zigzag for present here. And if I want a 30 degrees lag, 30 degrees lag in the sense, the higher voltage, the higher phase, the HV winding vector is at 1 o'clock and this is the 12 o'clock lag. So this can be get by, suppose if my YD1 or DY1, 1 o'clock, right? 1. 60 degrees lag in the sense, where you can see 60 degrees. Second, 2 o'clock, YD2, DD2. So in the similarly, 150 lag, YD5, DV5, and 30 degrees lead or 330 degrees lag, you can say YD11, DY11, like that. So these are the notations of the vector grouping. Generally, how they are connected. Now, the question is, yeah, please.
So my question: how we will decide that we have to go for the 30 degree?
Yes, that's what I'm that's what I'm explaining now. Yeah. So these are the different types of connections you can see. And if you Google it also, you can see how they are connected with 0 degrees, 30 degrees, 60 degrees. These are different types of connections. Now the main question is, why I require 30 degrees? Why should I go for a 60 degrees connection? So here, some important points we need to consider when we are selecting the vector group. Team, please mute your mic. Someone else. Fine. Cool. So again, I am stating the point. Vector groups identify the winding connections and polarities of the primary and secondary windings. From a vector group, one can determine the phase shift between the primary and secondary. So generally, why we should focus on the selection of the vector group? So generally, on what things the vector group depends on? The transformer vector group depends upon one, the harmonics, parallel operations, earth fault detections, and type of load and application. In a simple way, it was mentioned in the standards of IS 2026 that the transformers, that delta star connection, which is having 30 degrees phase shift, will nullifies the third harmonic. The winding, the star winding, nullifies the third harmonics, preventing it to be reflected on the delta side. That is this connection removes the harmonic string. Which one? Delta star connection. Please remember. Next point. Parallel operation. All the transformers, this already we know, every stage we are speaking about this. All the transformers should have same vector group and polarity of the winding. This already we know. Next, the earth fault detection. The delta transformer does not have any neutral. So in those cases, to restrict the earth faults in such systems where the delta transformers exist, we have to use other zigzag wound transformers to create a neutral along with this earth fault rings. By these delta transformers, we cannot detect the earth faults. So obviously, you have to again establish a connection with zigzag or using the neutral displacement relays by taking the open delta PT on the delta sites. If you are not if you are not much aware of this, then the best option go with the star-star connection of transformer. And come to the next one, type of non-linear loads. Non-linear loads, you already know. They won't form, you mean that the voltage and the current phenomena is not forming a linear relationship. These systems generally having different types of harmonics. You know that generally we can see a non-linear loads, furnaces, heaters, variable frequency drive systems. So in these cases, generally we will use delta star connections, delta star 11, delta star 5, these things. Sorry, delta star 1, delta star 11, like this. Because 30° phase shift nullifies those harmonic content to 0 in the supply system, because these harmonics are generating by these nonlinear loads of VFDVs or other finance heaters. And also, this vector groups also depends upon type of transformer application. Like, suppose generally for a power export transformer, that is generator side is connected to the delta and load side is connected to the star. Suppose for power import and export transformer, that is for transmission purpose, generally for substations, transformer star-star connection may be preferred. Because this will avoids a grounding transformer of the generator side, and also it's prefers to save the insulation for high voltages or maybe at the neutral level of the transformer. So by this thing, I can summarize you that where you can see a harmonic content in the system, prefer to go for a delta star for the auxiliary loads. If you are having application for generating stations, delta star is a good one. Delta star 0. Delta on the lower side. And if for the transformer substations, for the transmission substations, better to go with a star-star connection, because the 33 kV and above 132 kV, 220 kV, 400 kV, the level of the voltage is high. So if you have a delta connection there, the insulation cost is very, very high because the line voltage is equal to the phase voltage in delta connection. Where in the star connection, it is divided by 3, √3. So the insulation cost of that winding, if you go with a star, is cheaper than the delta connection. So in the higher voltages, star is the preferred one. And in the transmission substations, star is the preferred one, star-star transformers. And if you go into the generator side, delta star vibe is delta on the low, because the transformers, generally the generators will generate the power at low voltages like 11 kV, 13.8 kV, 15 kV. So not much, the insulation will not much, cost will more. So delta star is preferred there. And if you look into the loads, or auxiliary loads, we are having so many auxiliary loads, there would be chances of generation of these harmonics. So to nullify this from the star to delta, so preferred to, means this harmony should not reflect on the HV part of the system. So preferred is delta star.